So good afternoon, good evening, good morning, friends, from wherever in the world you are joining us today for this second in the series of CRES webinars. The subject of this afternoon for me here in the UK, apologies for those joining us from elsewhere, is plastics, friend or foe, to be given by Dr. Marloes Peters. Before I hand the floor over to Marloes, I just wanted to say a few words about CRES. The Society for Circular, Regenerative and Sustainable Systems. Hopefully you are familiar with us. If not, by all means, please go and check out our website after this event. There you'll find more information on our objectives, our structure, our targets, our objectives, and you can read for yourselves our vision and mission again, if you like. I just thought, where we are at the moment, just share my own views. At the moment, we're a collection of like-minded individuals sharing a similar vision, which is to integrate systems thinking into everyday decision-making. So although we are a society, we have no yet formal registered license structure. But this second webinar is in a series of events to grow the community. So we're a community, a small community, and we're aspiring to grow it over time. If you have views on how best that we might achieve our vision and our mission, by all means provide some feedback via the contact form on the Society's website. After today's event, you will be sent a feedback form by Martin, my colleague, so by all means provide feedback on the Society itself and how you think we might best achieve our objectives for the Society, as well as the content of the presentation itself. So just a few words there. I'll move on to some housekeeping items for today. So the webinar is being recorded and it will be uploaded to the Society's YouTube channel afterwards. Slides will be circulated together with a link to the recording and a feedback form. So please complete that feedback form. Please keep your microphones and video switched off and post questions. I think there's a Q&A box into the chat box, and I will raise those after Marloes' presentation. Our speaker will be using the Zoom polling function, which will be managed by my colleagues Martin and Sonia. So if you get lost or stuck at any point, please just feel free to log out and log back in again. I should, right at the beginning, of course, have introduced myself, so apologies for not having done that. My name is Dave Tompkins. I'm Head of Knowledge Exchange and Innovation for a UK-based wastewater consultancy called AquaEnviro. And AquaEnviro is part of the global SUEZ group of companies that you might have heard of. We're specifically part of SUEZ Smart Environment and Environmental Solutions, or SES. And it's my pleasure to facilitate today's webinar. What that means mostly is posing your questions to our speaker and making sure we stick to time. So without further ado, it gives me great pleasure to introduce today's speaker, and I'll read a brief biography. Dr. Marloes Peters graduated from Eindhoven University of Technology in the Netherlands with a degree in chemistry and chemical engineering, before moving on to the Institute for Materials Research at Hasselt University, where she completed her PhD as part of the biosensors group of Professor Wagner. There, together with Maastricht University, she developed polymer-based sensing platforms that were used for the electrochemical and thermal detection of neurotransmitters. Since March 2019, Marloes' research group has been based at Newcastle University here in the UK, where she is a senior lecturer in the School of Engineering Advanced Materials Group. This group focuses on developing novel polymer-based sensing platforms that can be used for environmental monitoring and sustainable healthcare. And in this talk, Marloes will focus on how polymers can be used for trace detection of antibiotics. So Marloes, the floor is yours. Thank you very much.
Thanks very much. Okay, so hopefully you can see my slides now. Well, first of all, thanks very much for the introduction, David. What I would really like to talk about today is I have a bit of a dual hat. I'm both based at Newcastle University, but I'm also a member of the IUPAC Polymer Division. And hopefully you all know about IUPAC, but what we also do in the IUPAC Polymer Division is promote the use of polymers, but also educate people on plastics and polymers. And what I would really like to talk about today is some of our recent work where we show that actually a lot of people have a very negative connotation around plastics. I think people think of plastic bags. We think of all the face masks currently that are lying around. But what I would like to show that there's also another side to it, where show how we can use these polymers for monitoring of environmental pollutants, but also how we can make new materials from recycled polymers. And if you want to contact me, you can see some of the contact information here, but also well, you can use the chat for questions, but also feel free to kind of introduce yourself in the chat, because it might be good to hear what your research interests are. Now, this has all been introduced, so I'm not kind of going to go through all the steps that I've had so far. But what I do think is important, what you might not directly see from this, is that I've had like a very multidisciplinary training. So I've been doing some work on more like pure chemistry, such as in my PhD, some chemical engineering, working with clinicians a lot at the moment, but then also some environmental analysis. So I think when it comes to tackling such complicated problems, you will see that a really multidisciplinary training is quite important, especially for early career researchers, I would say. We also have a big interest in science communication, so particularly myself, but hopefully my students are enthusiastic about it now as well. So if you want to hear more about the talk by my PhD student, Ollie, on smart sensors, then I think the link was somewhere in the abstract, so you can view it on our YouTube channel. Now, what are the kind of sensors that we think of before I go on to the polymers and the plastic bits? So we focus mainly on two different areas. And for now, I'm mainly going to focus on the thermal sensor that we have, which is a little portable device. And I'll show in a bit later what it actually looks like. But in the picture, you can kind of see the dimensions. So it's relatively small. It's like, well, you can definitely carry this. And we use that for detection of contamination. So whether that's, for instance, here you see a picture of E. coli in water, so microorganisms, antibiotics, but you could also think of contamination in food. What I'm not going to focus on in this talk, but what we are interested in is also where we look more at electrochemical detection, which is compatible with in vivo measurements that you can do in your body. And we've used polymer-based sensors that are integrated into catheters. So when people have a catheter in their intestines, we can directly measure things there, but also sensing of, for instance, inflammation and implants. So that's kind of the other part of the work. If you're interested in it, you should look at our publications. But the focus will be on how can we look at monitoring of environmental pollutants. And before I go on to exactly what we do, I wanted to briefly talk a little bit about like the history that we have with plastics. So even though if you think of the first use of like a natural polymer, it goes back to the Aztecs and the Mexicans that use these little rubber balls to play with. So you can really trace back the use of polymers a long time back, and they were very cunning in how they actually kind of managed to modify these natural polymers. Now, the Bakelite was the first industrial plastic that came to the market. And from then on, we said there was really a plastic revolution because you could shape it into any size and shape you wanted. It's cheap, it was durable, and it was suddenly accessible to everyone. But it wasn't until the publication of Staudinger in 1920 where they actually pitched how these polymers, what it actually looks like in terms of chemical structure, and that there was a linkage between them. Now, I think I don't have to tell you about like there was a huge rush in plastics, but the first actually report of plastic debris in the ocean was already dating back to the 1960s. So it's not so much of a new problem anymore, but obviously it's kind of grown a lot over the years. And we've all seen documentaries by David Attenborough. We've seen the example of the face masks. We look at potentially biodegradable bags. So there's a lot of things going on in plastics that are quite recent. Now, and because this is a webinar, and obviously it's kind of nice to get your opinions as well, what I would like to do, and to also make it hopefully a little bit more interactive, because for me, for instance, it's very difficult to see the chat at the moment. But I've prepared a very, very short poll. It only has 3 questions, so please do kind of engage with it. There's no right, there's no wrong answer. So someone, yes, there we go. You can see that the poll was launched. So hopefully it would be good to hear your feedback on it. And it's all a little bit about like your view on polymers and plastics, and also linking to water quality, because I'm also going to talk about that. And you will see that this does link back, and this presentation will link back to a lot of the UN Sustainable Development Goals. So a lot about climate action, life in the water, obviously, but also life for us, pollution, etc. So I'm going to give myself a little break, have a bit of water. So in the meantime, if you could have a quick look at those questions. I can't see how many of you have filled them out, but like someone from CRES will surely be on top of it. So I'll do it myself now as well. And would just be good, it's also to stimulate a little bit of discussion. So we'll wait 1 or 2 minutes, because hopefully you can fill out this fairly quickly, so we can have a look at it. I can't see how many of you have filled it out, but I presume someone will is able to share the answers as soon as at least the majority has done that. So I'll patiently wait for that. And as I said before, there's really no right or wrong here, particularly when we look at water quality. So it would just be interesting, like I'm also kind of drinking some water now, for you to see what you value in your drinking water. Okay, I don't know if anyone can tell me if the majority of you have filled out the questions or?
And so at the moment, we have 66% of the participants fill out the questions. So
that's not too bad, but I'll give you 1 more minute. It's and and I can already see, I can briefly look at the chat now. That's the good thing about this. Decide what will happen to the huge pile of plastic that's being dumped into the oceans. Well, if it's already there, it's very tricky, isn't it? So I'll definitely come back to that in the next slide, actually, because it is a very big problem. So I'll talk a little bit about how we can all really do our best in order to kind of reduce the amount of plastic. And I think you will see that it's not just a technology aspect of it, but it's also a lot of things that consumers will need to take responsibility for. Right. Do you think we can share the results of the poll, just to might give you an idea of what other people have done there?
Sure, I'll end the polling now.
Okay. And then I can go on to the next slide, where I'll kind of introduce some of the concepts to you here.
Yeah.
Okay. Good. So I'll go on to the next slide. So hopefully you can see. Okay, I don't know if I need to close my poll results. So I'll just briefly summarize the results for you that you can see now. So the majority of you seems to think it's 12%, mostly positive view on plastics, and main indicators of water quality. Well, dissolved oxygen is a front runner there, but I can tell you that all of them are quite important. Right. So I'm thinking. Okay, so I should be able to go on to the next slide. Great, perfect. So I think with a lot of us obviously working, you know, as researchers, I think if I do these kind of polls with the general public, you will see that the majority will not say it's positive. And a lot of people don't realize, for instance, like the contact lenses that I'm wearing, you know, are made out of plastics. It's our clothes, it's everywhere around us. And the majority of people do kind of associate plastic with plastic bags, etc. So it's kind of interesting to see how that varies a lot. One of the main problems of plastics, it's not like 99% is still made out of fossil fuels. It's not exactly 12% as you thought. I think it's a little bit lower, even though I found conflicting numbers. So it seems to vary a little bit between 4 to 8% of plastics that are responsible for greenhouse gas emissions. But a really key problem, and this is actually picked up in the chat, is that a very damning statistic that you will read is that they say that in 2050 there will be more plastic in the ocean than fish. So that tells you that there's a major problem here. So there are a lot of companies that are also kind of committing to reducing the amount of plastics. But likewise, plastics are important in medicine. And what it really is necessary is to look at how we can use, particularly into recycling. Now, what this comes back to, so I say, yes, I do use polymers and plastics to develop some of the sensors, but I will show you that there are ways of how we can use a circular economy approach. So we can use these sensors, for instance, from recycled materials. So when we do this, what we don't want to do is generate more plastic rubbish. So think of, for instance, in the UK, you do these lateral flow tests, and I kind of worry a little bit that there's, you know, even though it's for a good cause, that you're generating more waste as a result. Now, what I wanted to highlight here, this is actually done by my colleagues in Manchester Metropolitan University, but I think this is like a really nice project that fits in it with it quite well. And it's called Transform, and what they do is they use, for instance, PET and ABS, so plastic waste bottles, they collect them and they turn them into resin that's used for 3D printing. So some of the objects that you can see in that table are made using 3D printed waste filaments, so filament out of waste. And these are maybe not, like you can see like a Pokemon there, not the most useful objects, but you could imagine like 3D printing is quite a big thing nowadays. They even print like concrete, whole houses, whole structures. So there is a way, and they actually have, I've been there, and it's like tons of those filaments. It's not like, you know, it's plastic bags that I can't carry. So there's definitely a way of how we could use these plastics and transform it into something that's useful. So I just briefly wanted to highlight that here. Now, what is the main aim of like my project in the sense of the sensors that I look at? And we look at tackling a really complicated problem related to antimicrobial resistance. And what we would like to do is to have like a whole loop approach where we look at antibiotic traces in water, because antibiotic traces can accelerate antimicrobial resistance. But ideally, we would also like to see if those changes in microorganisms, if we can monitor the bacteria as well. So can we simultaneously look at how certain parameters, so this is even other stresses, like for instance, high temperature, high pH, or other presence of other pharmaceuticals, how can they influence bacteria, microorganisms, how they can actually get antimicrobial resistant properties. And what's a little bit different about this project is that we use potentially reusable sensors. We use portable sensors. So you would be able to take them on site and you would be able to do the measurement at the source where you want to do it, which is at the moment really complicated. I can tell you that. Imagine going into like a wastewater plant or going to a remote area, like just going to a river somewhere. You know, you would need to go into the lab to actually get your results. And ideally, and this is the last bit is a little bit far away from what we're doing, but we would like to make those using polymers that are made from recycled materials. And this lovely image is kind of the vision that we had of how we need to monitor antimicrobial resistance as a kind of wholesome approach. So we need to measure both antibiotics and bacteria. But the key thing here is that you need to look at doing this on site. So the whole chain is kind of connected, as you can see, and the red arrows indicates where basically antibiotics or other markers that can trigger AMR that go in. And you will see that the water, this is all kind of connected. And then obviously it's supposed to go out with wastewater treatment, but we also know that this is often kind of incomplete. And if you think of, you know, the water that you're drinking, there's actually not that much legislation on it in terms of like the compounds that can be present in there. Even though, for instance, in milk, there's very strict requirements on maximal residual levels. It's definitely not the case for water. So if you look into what I see as the cleanest water in Europe, I think of the Swiss lakes. Even there you can find traces of, for instance, your caffeine. So your coffee that you're drinking and that you might pour down the drain, which is for us totally fine. You know, a little bit of traces of caffeine is not going to harm us. But we do know, for instance, that it can be trigger for aquatic life. So for instance, it can cause some inflammation in mollusks that need to adhere to sites. So we need to think about some of the traces that we have in the water that has a clear impact on aquatic life as well. And for instance, we also know that the fish sometimes can become a bit slow because there's also a presence of, for instance, certain pharmaceuticals such as antidepressants. So all the waste that we have has an impact further down the line. And the way we do this is a little bit different in the sense that we don't use antibody-based systems. So most kind of sensors, I wouldn't say most, are based on natural recognition elements, such as, for instance, antibodies or enzymes. So in our body, we've got amazing sensors itself that are able to detect foreign invaders. That's what antibodies do, for instance, such as, you know, with viruses. But there's a lot of drive to go towards antibody mimetics. So which are compounds that have a completely different structure, but are supposed to have a similar affinity for what you want to detect. And you can see the structure of the antibody on the right. And what we do is we don't mimic the structure at all, but we mimic the interactions that the antibody has with the antigen. So we look at the non-covalent interactions between the two. And there's different antibody mimetics you can think of. You can think of aptamers, molecular machines that won the Nobel Prize a few years back. My focus will be on molecularly imprinted polymers. So this is where the polymers and the plastics come in. And the reason for doing that is that they're extremely cheap. They're not sensitive to changes in pH and temperature, or not so much. So you could even think of measuring at temperatures of 70 degrees, very acidic media, things like this. But what's also important in terms of sustainability is that there's a lot of waste of resources when you use antibodies, because there's a lot of variation between them. The validation is less than perfect. And what people sometimes are not so aware of is that also, even though we've got recombinant antibody technology, there's still about 1 million animals per year that are used to generate antibodies for diagnostic tests. And the EU has issued a ban now on animal-derived antibodies. So it's definitely like a hot topic to move away from these animal-derived structures. Now, this is the main concept. It's like, think of, I was talking about these molecularly imprinted polymers. And if you think of imprinting the way I explain it to my students, it's like we have a biological memory. So when something hatches from an egg, the first thing that it sees, supposedly its parents, it would kind of like bond with that and remember that. Polymers similarly have molecular memory. So what we do is we take something that we want to detect, and that's what we call the target. So if this is an antibiotic, this is an antibiotic. If it's a bacteria, we can start off with the bacteria or something similar to the bacteria. We assemble some monomers around it that can interact with the target, and then we polymerize it. So as soon as you polymerize it, you've got like a stable structure. Then you remove the target that you want to detect, and then you end up with these binding sites that have very high affinity for the target because they're similar both in size and shape. But they also have got some chemical interactions. So it's a combination between those interactions that makes them very selective towards what you want to detect. And the advantage mainly of this approach is that I said before, we can detect something really small, to as small as an ion, to small molecules such as antibiotics, but also going towards proteins and microorganisms. So we can look at a whole spectrum of different compounds. It's just if you adapt the polymer, you can look at different options. And there are some commercial options out there. So if you would be interested in, for instance, solid phase extraction and purification, then you can actually buy these polymers from Sigma Aldrich for a number of environmental contaminants. But for sensors, it's a little bit more complicated because you would need to integrate these materials into a sensor. And this is where we come in. And I will show that in general, the affinity is still lower than antibodies, but that we have approaches where we can start to compete with antibodies. And this is where the whole thing, like we've got these polymers, now we want to put them on the surface, but what kind of detection method do we use? And my lab is a little bit different in the sense that we've looked at some electrochemical detection, but I'll also show you this kind of a patented thermal device that we have. And if you think of it in this is more like an artistic view, no? So think of a polymer with some cavities in there that actually bind things. And you will see that as soon as you've got binding, so hopefully the animation will work, you will see that there's a change in the electrical resistance. So this is impedance spectroscopy, which is normally denoted with a Z. So what it means is that there's an increase in resistance on the surface once you get binding to these specific binding sites. I mean, we call this like a pore blocking model because you have pores, and once they're blocked, you see an increase in the resistance. Now, this is not something really new because people knew that there was a change in electrical resistance. But what they didn't know is that there's also a change in the thermal resistance, which are normally linked. And the way you should see this, you've got a surface, and if you pulse heat through, once you start blocking things on the surface, or when you add things that are less conductive, then you get a change in the resistance, also in the thermal resistance at the interface. So basically think of it that you've got lots of different holes there, and you add an insulating material to it. So then the temperature that you measure above it is going to go down. But what this looks like, you will see in a little bit. And first, I will tell you some of the challenges that we have, because obviously this links into this topic. We need to have a method which is scalable, so larger scale production, easy to make, and easy to make, you think of, for instance, the lateral flow tests now, you think of like a pregnancy test, you think of glucose sensing. But somehow one of the most problematic things for us, and they used to market this as plastic antibodies. And they've completely moved away from this because the term plastic was very negative for a lot of people. So, and because it's very different, it's not like a plastic copy of an antibody. This is not really used anymore. But how do you convince your customers to use plastic? And what is a real challenge here is that we are more like looking at portable sensors that are low cost, low weight, easy for you to take, but also easy to operate. So you wouldn't need to have like a lab technician doing a test for you. You would be able to see by the eye, is there something there? Is there something not there? And ideally also have an indication of the levels, for instance, antibiotics. And how my lab actually does this, we used to work with polymer microparticles, which have limited affinity compared to antibodies. So we started working with a company, MIP Diagnostics, who are UK based, and they have a scalable approach to produce polymers. But they produce them as nanoparticles. And the way the approach that they use has the advantage that they have a method that allows to make biocompatible materials, which are also very homogeneous, so they're similar in affinity. And potentially there is scope to use either biomaterials, so polymers made from biological sources, or recycled materials. And what we offer then is that we work with them in order to integrate them into our thermal and optical setup, which I will show in a bit what this looks like. So this is a really and I think also what you mentioned in this network, it's very important that we work here with industry in order to offer like a solution, which hopefully will have more uptake than you can generate as just a research group on your own. I know this video has a bit of sound, so don't be alarmed by it. It's just a bit of like catchy background music to wake you up. And this is a schematic of how this thermal setup works that we have in the lab, and then you will see what it actually looks like. Oh, I believe it should start now. I'll just stop here for a second. So this is the background music I was telling you about. Now our polymer layer is seen as the bit in green, which is on the top. So what we would like to do is to have, we compare this to like an espresso machine. You could have like with the green, we only want to detect the green in the solution. And we know that we have complex solutions. So what this polymer is supposed to do is only absorb the green from what you see. And then you should have a look at what happens to the temperature after we do this. But let's say if you wanted to detect the red in the solution or the blue in the solution, we would insert a different polymer and extract a different compound. So it's supposed to be like a platform technology, which in an ideal world, you would be able to integrate that into like an array so you can mix and match the compounds that you want to measure. But let's have a look and see what happens. So we send out a heat pulse now. And hopefully if you paid attention to what happened to the temperature, you could see that we pulsed in heat. So the temperature went up. And as soon as the green material bound to the green polymer, you saw this drop in temperature. And that's associated with this change in thermal resistance that we monitor. And this is all good, but this is like a nice schematic. What does it look like in the lab? We use flow cells, which before we used like a volume of around 2 to 3 milliliters, which is probably fine for water samples. But we also have a small setup that we only need 100 microliter, which is important if you want to measure blood samples, which is sometimes all you want to do. And in that flow cell on the left, we actually insert the polymer in there. So I'm not sure if you can see my mouse, but you would insert like a little functionalized chip that goes into the flow cell. And as I said, the volume in there is only 100 microliters. So this is really, really small. What we have at the moment is we've got like a little device, which is all made in red, which is a homemade thermal device that can control the temperature, but it also measures the temperature. And what it allows you to do is to have a certain temperature that you have like within like a heat sink, so a copper layer, and then we measure the temperature just below the sensor itself. And this temperature gradient is related to your thermal resistance. Now you will see that we've got a connected syringe pump to administer the samples, but we don't necessarily need to use that. It's just convenient if you want to automate everything. So you would even be able to program this from home. But ideally, we just want you to add a little sample within that flow cell and get your results. Now, the way this works from a more like fundamental perspective is that we have quite an innovative technique of how we produce these polymers, which we use using a solid phase approach. And if you want to know more about it, you can have a look at the papers here. So we first attach whatever we want to measure to like a glass bead. We polymerize around it, and then we can use the solid support as an affinity medium. So we use a certain elution based on temperature or other things. And then we only collect the particles that have a very high affinity for what we want to detect. And these nanoparticles, which at the moment are somewhere between 50 and 100 nanometer, but there's a bit of a drive to go even smaller. We can literally just, because they're in water, so they're water soluble, we can directly coat them onto surfaces. So we've used approaches such as simple dip coating to drop casting, and we have these nanoparticles for small molecules, such as this antibiotic vancomycin I mentioned. We have them for proteins, but you will also see later on, I have a little slide on how we use them for viruses and bacteria as well. Similar principle here. We have these nanoparticles around a thermocouple that measures the temperature. And as soon as we got binding to that thermocouple, you will see there's a change in temperature. And we've done this for a range of different molecules. So we all were able to detect all of them in a very low concentration range, so all in the nanomolar range, which is enough for a trace detection. If you would have a thermocouple not functionalized with anything at all, you would see no difference. So we add something to it, and you will see that the red line stays roughly the same. But when we've got really low concentrations of, for instance, like proteins like biotin and trypsin, we see a drop in the temperature, which is associated with this increase in thermal resistance. And what's the nice thing about this is that we can even measure in complex matrices. So we looked at saliva, we looked at blood, but even the water that you have in rivers or, for instance, in wastewater plants is very complex. It might even be more complex than blood samples, really. So this is a very important aspect. And thinking of it, if you just drop cast or dip coat a material on it, it's not that interesting because it's not necessarily the most reproducible. So if you go to a company, they're not necessarily happy with that. So what we have done is that we've taken that material and we used a different approach, which is also quite fast, but it's based on electrografting. And then we can really reproducibly add a lot of nanoparticles with a very high surface coverage. So surface coverage is like 80–90%. And if you don't know, well, hopefully in the SEM is not the nicest because it's on a carbon electrode where you have like lots of, it's not as nicely controlled as a gold surface. But hopefully you can see that the little dots are lots of nanoparticles that we have around. But the images we have on gold are a little bit better. Now, if you want to think of a more kind of sustainable aspect, and this is what these screen printed electrodes look like. On the top, you can print lots of them, so they can give me more electrodes than I can normally measure. And under the scanning electron microscope, you can see that this is a very rough surface. But normally they are printed onto polyester substrate. So in a way, you've got more, you have more plastic on what it's printed on than the little black dot, which is actually the carbon electrode itself. So very good for mass manufacturing, extremely cheap, which you can see here. And we did manage to use this for detection of a number of small molecules. And we were interested in caffeine because I said before, that's kind of, strangely enough, a bit of a marker for water quality because people drink coffee all around the globe. And that's normally something that should be easily removed by proper wastewater treatment. But what we've then shown is that we don't need to print on plastic. We can go to paper-based electrodes. So the polymers that we have, we mix them in with the black dots, which is the ink for the screen printing. We can use paper-based electrodes, and there's potential to regenerate these surfaces. So if you wash with a very mild solvent, even with soap, potentially you would be able to go to a reusable system, which is something that you normally don't want to think about. But if you could wash with, not with an organic solution, but something as simple as soap, then that has become, you know, obviously would lead to less use of these plastic sandwiches. Now, the key thing is here, I mentioned, okay, small molecules. So hopefully you're convinced that we can really use this for antibiotics, but can we also expand this to bacteria? And here I would say this is a lot more complex because the reason for it is that we depend on what's on the outside of the bacteria. So bacteria have sugar groups, for instance, on the outside, and you would have a bacterial community, which makes it a lot harder. And you probably also want to look at bacteria on surfaces, for instance, if you think of like a hospital. Now, we have shown that this is indeed possible. So we showed, for instance, and there are other groups working on this who looked at E. coli in urine. They looked at surfaces. They looked at apple juice, which has a lot of E. coli, which you know in some cases might lead to food poisoning. But the key thing here is we have a lot of E. coli in our gut as well. So how can this sensor discriminate between something which is normal and something that's pathogenic? And this is a little bit where the complication of this type of sensor comes in. That if we want to look at antimicrobial resistance, I would say that it's been very well established for small molecules. But so far, and this is from a few years back, I think we have made some progress. But when you look at the bigger molecules, the detection is still a lot based on size and shape, and it's very difficult to discriminate between different strains of the same. I will briefly show you, obviously, COVID-19, with the whole pandemic being very trendy, that we have done some work on viruses as well. But the reason for showing this is that there are ways of tackling the selectivity problem. And working with the bigger your molecule gets, the more complicated it is. So what we in general tend to do is to employ people working in computational modeling in order to help us with this problem. Because the way it works is there's an infinite number of polymers you can make, and you could ask PG students for years and years to produce different polymers, and then you would screen them, and then you would get the best performing ones. But obviously we need to speed up this process. So what we do at the moment is that we look at different epitopes on surfaces. So if you think of COVID-19, think of the spike receptor, or think of other antigens. So just to give you an example. And we can use some titration studies or chargers or interactions where we have a library of monomers, and then we check which one forms the best complex with the epitope on the surface. So we would allow them to kind of predict what monomers would be really good to use. And we have done some work on COVID-19 sensing as well, but what I want to kind of briefly show you is more the important graphs here is the polymers versus the antibodies. And this is a change in thermal resistance, where, okay, here it's difficult to see which one is which, but the bigger the increase in thermal resistance, the better the response is. So we can see that the polymers at the top line are definitely capable of binding, maybe better, but definitely comparable compared to the antibodies. And the other thing is where you look at the AFM images, is that we expose them to quite high temperatures. So we expose them to 50 degrees. And our particles, you can see, are not changing at all in diameter. So they are really stable. And what we're kind of trying to look at now is there's obviously serious limitations in situations where you can use these antibodies to measure. But there start to be like applications, think of, for instance, measurement in sewage, where these polymers might be really offer really interesting prospects of in situ monitoring. And also the way we have to sell this, if we use this computational modeling and there are mutations occurring, we might be easier able to adapt these polymers rather than antibodies where you have to start from scratch again. So what's the kind of outlook from this talk? If you haven't heard about molecularly imprinted polymers before, I hope I've shown to you what why they're so versatile and why I hope to see more of them in the future, also particularly in commercial applications. Our thermal sensing is also something you probably haven't come across, but there's definitely scope for screening purposes, particularly when you want to look at like low cost and simple methods. But the MIPs do not necessarily need to be combined with this thermal sensing. So we also have incorporated fluorescent probes into these polymers, so we can look at optical detection or electrical detection. And this is what we're pursuing with companies in order to see how we can integrate this into commercial setups. So think of, for instance, if you already have the lateral flow technology, can we directly replace these polymers, these antibodies with polymers? Now, obviously, because this is all on plastics and circular economy, I haven't talked about it so much because I know this will be the most kind of challenging aspect. We do know that we can use a lot of biocompatible monomers, and we know that they've been used in animals and they've been used for drug delivery. So if we can use them in vivo, hopefully that will show you that, you can certainly use biomaterials. You are limiting your choices in terms of monomers, but there's scope to look at these type of materials. And more importantly, and also to increase that commercial aspect. There are, like you might have heard of aptamers, which is another synthetic alternative. There's ways of combining these MIPs with, for instance, quantum dots for imaging. So there's a lot of scope of not just using the polymers on its own, but combining it with other things. And what will be more challenging for us, and this is particularly what we're looking at in a project when we look at studying inflammation, we would like to use either biomaterials or biodegradable materials. So for instance, if you would have something where you only want to measure for the first 6 months whether you have inflammation coming from a cochlear implant, could we use these biodegradable materials, such as, for instance, polylactic acid, to monitor things? Now, I'm hopeful that, and this is, I should have acknowledged my research group in the beginning, but here you see a little picture of us working at Newcastle University. I think you will have seen that this is quite like a big collaboration, both between industry, which is mainly with MIP diagnostics, but also a lot of other universities, both in the UK and in Europe. So what we kind of would like to do is to show that we can actually use these polymers and that they can be a sustainable alternative. And what I would like to see is less, sensors that we can just use once and then throw away. So either some sensors that are made from recyclable materials or sensors that we can use more often. So that was all of it from me, and hopefully there are like some questions for you in the chat. I can look at the chat, but I'm hoping you can read out the questions, David. This makes it a little bit easier.
Sorry, minor technical hitch there, Marlies. I do apologize. Hopefully you can hear me now.
I can, yeah.
Perfect, thank you. So yeah, we have a very interesting question in the chat, which before I get to that though, I'm just going to start with a kind of a slightly bigger question.
Yep.
You flagged right at the beginning that there are, let's say, market perception issues around the use of plastics in the environment. And I wondered how significant that was for your commercial partners and the direction of the research that you're having to take.
Well, it meant that they completely don't brand it as plastics anymore. It's branded as nanoparticles. So I would say it's quite significant. I think the other thing is you have to imagine is that you need to convince people to use them. So you really need to, the performance can't just be the same. It needs to be like at least 10 times better and cheaper. And it needs to be almost like a killer application where people are going to use this, almost like you need to go above like a big hurdle before you go there. But I know that it would never be marketed as plastics or as polymers even. So yes, big problems there.
Yeah, and in terms of market positioning, are you nearly at that kind of killer app point? I'm just kind of thinking, what is your technology replacing? And I'm assuming it's sending a person to the field, taking a sample, bringing that back to a lab, doing a series of preparation, rather than just something very simple you could deploy in the environment directly.
Yeah, I think when it comes to my thermal device, it's a little bit complex because obviously it's quite like, it's not someone that everyone else would have at home, no? So we do have a patent where we use thermistors, which is, resistors based on thermal changes. And that's a little bit further away because it's sensitive to changes in ambient temperature, which is a bit of a problem we need to tackle. I would say that our commercial partner is very, well, they already have products on the market just based on the polymers itself. So I do suspect, and they've got quite significant investments, particularly for COVID-19. So I think when it comes to the polymers itself, I think there will be a lot more on the market, but I think the main will be still in extraction and purification, because you're not competing with such an obvious alternative.
Thank you. Perfect. Yeah, we ourselves as a business are deploying wastewater epidemiology, so DNA, RNA techniques. So yeah, there are other ways to come at the question, and that, of course, we've seen very significant advances in downsizing the equipment that's required to do that, the portability of the equipment that's designed to do that. So yeah, lots of development across the areas. So I'll move to the question from Rob Chadwick at University of Strathclyde. He's about to finish his PhD in biocatalytic polymerizations. Could you use glycopolymers to enhance the specificity for bacterial detection?
Yeah, I do actually have a shared PhD student starting on the topic, and you're absolutely right. Obviously, I said the sugar groups, particularly when you look at, it's not just cancer cells, but also antimicrobial resistance, we know there are changes in the sugar groups on the surface. So glycopolymers are a really interesting alternative. I think, we would be really keen to, the thing is, it's a bit harder to produce them for us, particularly in my group. I don't have a lot of hardcore polymer chemists in my group, but I would say we know that glycopolymers can also be used for detection of bacteria. And what I would like to see is, I don't know if people already, when you do this computational modeling with the epitopes that we use in our library of monomers is quite straightforward. So it probably would be good to have, like, if you would have a similar approach with the computational modeling and what type of glycopolymers to use. And someone to really, really make them in a very controlled way. I would see a lot of scope for that for using for bacterial detection, definitely. Yeah. For small molecules, I don't think it's as necessary, but I think glycopolymers would be very interesting for bacterial detection.
Thank you. That sounds to me as though it's a postdoctoral conversation at the very at the very least. So yeah, please contact one another. That'd be fantastic. A question from colleagues, and it's the same as a question I've noted myself. It's are the sensors single use, or can they be kind of refreshed, replenished, cleaned, and reused?
Yeah. So I the problem is that we would have, when it comes to medical diagnostics, you probably want a single-use sensor. So there's no way I could convince anyone in medical diagnostics, and also in terms of health and safety, that they want to look at this aspect. Okay, so that's the first aspect. But when it comes to reusability, we have shown that for the bacteria that we can wash them with soap because it kills off the bacteria, and then we wash with water. So that is possible. The only question you need to ask yourself then is the washing step that you do, because you also need to use water, is that actually worth doing? You know, you really need to have this whole, like, what they call like cradle to cradle, etc. approach. Like, is the washing actually the benefit of, rather than using another sensor, if that sensor potentially is degradable? We have shown so far that we can reuse it up to 3 to 5 times. I think that is kind of starting to stretch it a little bit. So that's, you can find some reports on that. Not more than that at the moment, unfortunately.
Sure. And is anyone in your group or elsewhere looking at that kind of cradle to cradle piece, just to bring the wider sustainability questions to the table?
I would say that's more with the people that we collaborate with. I'm definitely interested in it, but this whole techno-economic analysis is a little bit outside my own field. But we would be really interested for people for looking at this for us, because for environmental monitoring is actually, we've mainly focused on healthcare applications where this is not so much an issue. But for monitoring, yes, it would be really interesting to know.
And of course, I have to plug systems approaches here. So if you then add in some of your natural polymers, your chitosans, your other potential substrates and components for the system, then yeah, the number of questions expands very rapidly.
Yes, it does. Yeah.
So a question from me is how long are your sensors? So in an environmental application, and my work is largely wastewater. So yeah. How long could you leave the sample out before you'd take your reading? And then are you seeing any shedding of those nanoparticles in use in application in the field? Yeah,
so fouling is the single biggest problem in sensors, no? And so you would get fouling over time. So we know when we use to dip coat the sensors or drop cast them, yes, we see shedding of the nanoparticles, no doubt. Not in hours, but in days, which we used to track because we had some fluorescent probes and we would literally just see it coming off. We are testing now with the electrografting, where we're also looking at what's the best way of storing them. And actually the particles, they swell in water, so they're quite like water. So that's kind of an advantage in a way. So I would be comfortable to say that storing, having the particles in water, I think we can, well, it's obviously we're testing. I'm quite confident they will remain on the surface for quite a long time. The only concern I would have, and this is more of a matter of how you would kind of reduce them, or if there's a way of how you can recalibrate them, is that I would worry maybe a little bit that the binding sites would be blocked with things as you go along. So in a way, it might be more for environmental monitoring easier if you would, ideally would have something in situ, but if you would take a sample and then just drop it on the polymers and then see what happens. But yeah, all very good questions and things that we need to think about.
Thank you. So there's one more question in the chat which I'll raise, and then I'll conclude with a final question from myself, if that's okay.
Yeah.
So the question from the chat is from Amran. Thank you for that question. Can you attach antibodies directly onto your polymer?
I don't know. We've never looked at it. I know that it's not so common to do it with antibodies. I know you can incorporate aptamers, etc., in there. But I wouldn't see why not, because you can really use very straightforward coupling techniques such as EDC coupling, because they have got acidic groups, they got free amines, so there certainly should be scope for attaching things to them. Well, I have never looked at it because we're trying to replace antibodies, but yeah, there might be an application for it.
Great, thank you. So a final question from me. Apologies, it's me with my consultant hat on. And are you seeing the market going in a particular direction in terms of the kinds of things it wants to monitor in the environment? Of course, COVID, I'm sure, is very popular at the moment, but in more general terms, are you seeing the market move towards antimicrobials or metal hazards, or what does the outlook look like? Okay,
I know this from a funding perspective. Okay, so I know that like when I apply for funding myself, everything that's been related to antimicrobial resistance has been very well received. So anything with antibiotic residues or anything else that can cause antimicrobial resistance, we've had quite a lot of success with that. Not so much with anything related to neurotransmitters, and clinicians are definitely a little bit wary of using alternative to antibodies. So in the market, what people are more willing to kind of try something new. I've been, for instance, looking at hormones, other micropollutants in water. So I think there's and in the food industry, there's also been a big demand for screening of samples. So if you look at, for instance, E. coli detection in water, they're not that interested in it. But like there are companies that's, because in the food industry, the way it normally works, they send out their samples, they test it in the lab, and they have to recall it afterwards. So I think like the food industry would be quite an interesting one, and that's obviously what we're kind of trying to look at now. And they seem to be more receptive to changes compared to medical partners.
Excellent. I'm certainly very interested. We're looking at kind of supply chain transparency, accountability, quality, monitoring, all those kind of things. So yeah, I'll be getting in touch.
Yeah, I mean, everyone here, well, thanks. I know for some of you, it might be really, I don't know, late or early. So I think you've got my contact details, so feel free to get in touch.
Fantastic. So Marluz, it's up to me now just to thank you once again for that fantastic presentation. Thank you for taking our questions. Our time is up. There are 1 or 2 questions left in the chat. So if my CRES colleagues could save down the chat, then we'll get those sent across to you afterwards and then circulate with the materials afterwards. But for me, thank you very much indeed.
Okay, well, thanks very much.
And thanks everybody for taking part, and we'll see you soon.